Okay, welcome to Saturday morning tonic, live session 6, Pythagoras and trigonometry. And I hope I've given you some questions here that are fairly challenging, enough to come and see how you sort them out. And we're going to be looking at Pythagoras in 2D, Pythagoras in 3D, trigonometric ratios, and we can't get rid of that, can you? And bearings. Now, bearings are one of those applications of parallel lines and trigonometry and Pythagoras that are very good to know, because that's generally like the real life application that will be in an exam. So let's have a go. 61 days to go. It's not really very long at all, is there? Sorry about being a bit late today. I have these new headphones. They are the Sony XM5s, okay, WH1000 XM5s. I'm going to link them in the description if you're interested to see which ones they are. And I absolutely adore them, but this is the first time I've tried to go live with them, and something very strange happened. I just hope right now that audio is coming out of YouTube fine. In fact, it might be good to just test. So bear with me in 1 second. I think that sounds good. I don't know if you heard me, but got myself up on the old live stream on my phone, and I think I'm sounding pretty normal. So let's go for it. What else do we want to say? I want to say that if you go to Patreon, I know it seems a little bit intimidating. It's a whole new website, but you can really trust them. They're just a standard website, just like YouTube. There's nothing like sinister in a sense. If you go on there and it will say, oh, sign up for a certain amount of money, you don't have to. I've made all of the content for these live streams absolutely free, with no need to even sign in or make an account. But go there, and half an hour after this live stream you can get next week's questions to have a go at. You know, they're not going to happen overnight, and you don't want to be doing them first time when you're in the live stream or watching the video, because that's not the best way to approach learning. It's your journey. You have to go through it yourself, and you're going to learn a lot more by making some mistakes before you figure out exactly how it works. Okay, so go to Patreon to get those worksheets, and you can backdate. You know, you can look at the previous ones. You'll also find on there a guide to GCSE, and I've included some really important foundational topics and a guide to passing GCSE Higher. I'm not going to say it's in it for any particular exam board, but it's just in general, for that level, there are certain skills that I think you can't really get away with not knowing. All right, good to see you, and thanks for being here. Thank yourself for being here. Congratulations. This is important, and you're really stepping up for yourself to make the effort to be here. So I appreciate that, and let's get on. So if a triangle has the sides 14, 48, and 50 centimeters, question is it a right angle triangle, and how do you know? Well, there are certain relationships that have been found in right angle triangles. Typically, you'll be given a right angle triangle, and you would assume that Pythagoras is true. You trust it. You've been told to trust it, or maybe you've discovered that those properties are true. It can work the other way around as well, as a test, which you might not have seen, that if you want to know if it's right angled, is it a right angle triangle, the Pythagoras will be true for it. Now we know we need to identify the largest number. So if we just remind ourselves of, let's make that a wee bit smaller. Where do we have it normally? Maybe that's fine. If we remind ourselves of the formula, we have a squared, which is a small side, plus b squared, another small side, equals c squared. That's the largest side. And if we put that into our equation, like the numbers that we have, this is clearly the largest. Doesn't matter which way round the other two go, because essentially you can do them in any order. You're adding the result together. It's going to be the same no matter which way round. What we're going to do is see if the left-hand side is equal to the right. That essentially is equating, right? You've got it equal. So 14 squared. We've got time to do this properly. If you haven't got a calculator, let me be your calculator now. And 48 squared is 2,304. And the question is that, when we add them together, equal to 50 squared? 50 squared is 2,500. You're probably looking, thinking, that does look pretty sneakily similar. 2,500, if we add that together, it's true. So, yes is the answer. And that's because Pythagoras' theorem holds. Now let's have a quick talk about Pythagoras' theorem. This is simply the Greek fellow that decided to put his name to the theorem. I think it's been around for a long time. I think it was discovered by a certain person. Now, I'm not sure how rich Pythagoras got off of putting his name on this, but we do certainly say his name a lot, don't we? I'm not jealous, no. It's just to put your name on something. Just imagine you did that now. It's either for money or it's something else, and I guess it's a bigger debate. Anyone's interested in a really interesting conversation in maths, then would be talking about whether maths is invented or discovered. Hey, let me know what you think in the comments. All right, calculate the area of a regular hexagon whose edges are 9 centimeters. Why am I American? I'm not. Label what we have. Label what you got, what they tell you. Okay, I may have gone over the top there, but essentially, if it's regular, all of those edges are going to be the same. And let me just readjust my microphone down a bit. Yeah, then I can carry on looking at my question, because currently I'm just having to look up to talk. That's right, so they're all the same, but there's something really important that we must know about regular hexagons. And that is the property that all of these lines that I'm about to draw are going to create equilateral triangles. A hexagon is made up of 6 equilateral triangles, which is essential for what we're about to do. It means that we can talk about all of these angles inside being 60. So area of a regular hexagon, why is that important? I actually did a really cool little short video like looking at this, and I might link it somewhere if I can imagine to do it, but essentially all of these can turn into right triangles. Let's pick the bottom one just because it's easy. If we split it down the bottom, then we could turn it to a right triangle. I'm going to stop there because I just realized maybe you don't even know why I've done that. Like, to me it's obvious, but why did I do that? Well, let's think about what we're trying to do. The area of a regular hexagon. We wanted to find, like, I told you about the fact that each of these turn into like equilateral triangles. And the next step would be to find the area of maybe one of those triangles, because then we can multiply it by 6. So I'm thinking to myself, if I've got myself a regular triangle and it's 9, 9, 9, I could just do 9 times 9 and then divide it by 2. Yeah, you guessed. This is a big mistake. This is what a lot of people get wrong. I think it's too easy to learn it and think, oh, well, I'm just going to pick the side that looks like it's the height. But we should learn it in this way, that it's not the length, the numbers that you're given in the question. You have to question whether what you've been given is the perpendicular height. We'll call that x for now. And if you're going to split a triangle straight down the middle, equilateral, you're going to have to halve this here. So now if we focus on the right hand side, we have an we have a right triangle. The reason I want to split it down the middle is because that perpendicular height is essential for finding the area of this triangle. We can now use trigonometry or whatever it is we need to do to get this. Now, if you halve the angle at the top, if you do that drop down the middle, what is usually 60 degrees will be split into two, and actually becomes 30. But what I'm going to say here is, if you don't have to use trigonometry, then don't use it. I can see that we can get away with Pythagoras here, which is generally easier and something that you could possibly get away with without a calculator. Let's do it with a calculator to begin with. So ignore the fact that there's an angle in there. We would have 9 squared, which is the long side, subtract off 4.5 squared. And then this would equal x. Now, if you don't know the formula, it essentially isn't as straightforward as that. That's me cheating, I suppose. Let's do it properly. 4.5 squared plus x squared is equal to 9 squared. This is essentially it. But what I've done is I've rearranged it. So I've moved the x over there, so by subtracting x squared from both sides, and put the 9 squared over this side by subtracting 9 squared from both sides. In fact, it's probably a little bit more simpler than that. Let's just move this over to the other side. That's much simpler. Okay, so if we move that over, we've subtracted 4.5 squared from both sides. Let's just write that to make it clear. 9 squared subtract 4.5 squared. And then I've square rooted both sides to end up with this, where we currently are. Okie dokie. Let's get rid of that in case we need the space. And so you'll find in Pythagoras at GCSE, there's only two scenarios. You're either trying to find the small side, which we are here, and therefore it's a takeaway, or you are trying to find the big side, and you are going to add them together. But bear in mind that it's always the large one, take away the small one, in the case you're trying to find what we're trying to find. Time to put it in the calculator. Press the square root button, 9 squared button, subtract 4.5 squared button equals something beautiful. Look at this. So x is 9 root 3 over 2, which is a wholly better number. You know me, I love those surds, but 7.794, etc., is going to be that number. I'm going to be using the exact number, because I can put that in a calculator fairly easily and give the full number of accuracy, and I'm not going to give up on anything. Time to use x properly, because it's looking like an x, like a multiply. Righty then, so we wanted this. This is the perpendicular height of the triangle, because we're trying to find the area of this triangle. And the area is going to be base. So I'm going to wrap a cord around my microphone, because it's really in my face. I decided, due to Bluetooth issues with this new microphone, that I would use the supplied cable with the Sony XM5s, and different sort of cable than I'm used to. It's fresh, so it's a bit curly. Okay, where were we? Cable, get out of the way. We were saying we want to find the area of this triangle, so it's perpendicular height multiplied by the base length divided by 2. We can call that area. And so the area is going to be 9 root 3 over 2 times by the entire base, which is 9, and then over 2. So it shouldn't take too long to put that back in, remember you can employ like use of, in your calculator you can have the answer button. So one area, I'm going to put the area in a nice neat form. So area of, how should we put this? Area of one triangle is going to be 81 root 3 over 4. Now, if you've got one of those calculators, the Casio, like the new ones, or anything from the 83 GTX onwards, you're going to get an answer in this form, which is much neater. If you press S to D button, you will get a decimal, which looks like this, 074, etc., etc. That's the area of one of them. I'm not going to use the decimal because it's weak. It's I'm gonna leave it on my calculator and multiply it by 6 because I've got 6 of those things. So 6 times the area of 1 equals, and now it's time to go to decimal, 210.4. Each side is in centimeters, so we're in centimeters squared, and that was rounded to 1 decimal place because it does carry on. And that's it. That's the area of a regular hexagon with sides of 9. So we used a bit of Pythagoras there. If you're surprised to see it in this question, so am I. No, I'm not. I made the question. Right, find the length marked h in the following diagram. Not drawn to scale. I should think not. So for this question, I gave you a few hints. I said, what about perpendicular bisection and area? So quite important is perpendicular bisection here. If you can remember what that is, it's where you have a straight line, and let's say you mark a compass from this point and here, and you draw a line like this, and then you keep that same length and you go from the other side, and then you draw a line like this, and then what you'll find is that this line that goes from here and perpendicular to this line is a bisection of the original line. Okay, so essentially you could draw like a triangle like this, and considering this would be isosceles, this will go straight through, this line in the middle goes straight through that middle. So this side is the same length as that side. Useful. The other thing here, the hint, was area. So in this case, it's going to be really useful to find the area of this triangle, perhaps in order to solve it. So I guess it's definitely not drawn to scale because it just doesn't look like these two lines here and here are the same. And that's, because it's the original document. I may be careful there. And that's where you're going to get the problem here. Like, I guess, like trying to visualize because it doesn't look like it is. But let's focus on what we do have. And we have that this is an isosceles. Now, if there is a straight line and this line is equal to this line, then this is 20 and this is 20 here, which is kind of useful. What else have we got? In fact, this 20, I just want to think about this. Yeah, because it's a dotted line, that 20 goes all the way back to that, like the base. I'm just going to do this here because it's not like split here with a hard line, and so that's like, I guess that's another thing to know. 24 centimeters there. So if we find the length marked here, we'd call that the perpendicular height. So I just draw it again here. So if that's the perpendicular height, and this is now defined as the base, then it would be really useful we could find that height so long as we knew like the area. So there's a couple of different ways. Hold on, this blooming microphone. Right, give me a second. Just gonna be right back a second. Okay, I think that's figured it now. Am I too loud? Too quiet now? Anyway, so there's a couple of hints there that will hopefully sort you out. Right, where were we? Yeah, that's it. So we're talking about this being 20 centimeters down here as well. And so this is an isosceles. We can draw our own little thing down here. And because it's isosceles, that's going to bisect this bottom part. So we can have that this area here, sorry, not area, this part of the triangle can be used to find the area in total, because this side is going to be half of the 24 because it's like a bisection. That said, we can then use Pythagoras. So we've got 12 squared, and we're going to subtract that from 20 squared, which is the longest side, and then square root it, which is going to give us, we'll call this side, what letter never gets used? F. No, well, sometimes it does. There are some letters that very rarely get used, especially in exams. We'll call it F. So what do we have? We have 20 squared, subtract 12 squared, and then square rooted is a very beautiful 16. So it has a height of 16 in this direction, which is in fact a perpendicular height, and therefore we can find the area of this triangle, which is going to be 16 multiplied by the base, which in this case is 24, divided by 2. There's a neat trick without a calculator. You can just halve one of them and say 8 times 24 is the same answer, but we have a calculator, so 16 times 24 over 2 is 192. So that's the area of this, and then we're going to use that fact and go back to the other side. So just going to get rid of this stuff now. Like that. And going to reverse this around and now pretend that this is the base, not this, which it just was for my drop line here. And in this case, we know the area is equal to a half times the perpendicular height, which is literally this letter here, multiplied by the base, which in this case is now 20. Let's put B, and then we'll put in what we've got. We've got that that's 192, and we don't know h, that's what we want, and then the base is 20. Don't make it look like 26. That's really cool, right? This is now an equation that we can rearrange. So we could take 192 on the calculator, multiply it by 2, and divide it by 20, and shabam, we've got the height is 19.2 centimeters. Love that question. You are essentially using a number of different things to get to this result, but it kind of forces you to look at the triangle in a different way first. Great to show that maybe the question is simple at first, but maybe it's deeper than it looks. All right, that's it for that page. Good job. I'm interested how you're going with these questions. Are you getting them first time? They're definitely going to make you think at first anyway. All of that thinking is really important stuff. And that's what the exam's all about, you know, seeing things you've never seen before, and making sure that you try and do as much of that before the real thing as possible. Talk about this one. So the pinball wizard game has an opaque tunnel. That means you can't see through it, where a ball exits directly below where it entered. It takes a diagonal route around the tunnel, and it enters the tunnel at 2,682 centimeters per second. How long does the player not see the ball for? Well, if you've ever played a pinball game, that's quite rare these days. It's all digital, but essentially you know this thing goes fast. In fact, it can go up to 90 miles an hour. So that's super fast on such a small little thing. And it's not going to be in there long. But such is the mathematics. When the numbers are beyond our intuition, that's when we have to rely on and be very consistent with the method. And the method doesn't always give us numbers that we can grasp, but we have to trust it, because that's how, that's how we make inference. So let's have a little look. We've got a very strange tunnel, and this is pretty awesome actually. If it goes in diagonally like this and leaves where it came out, essentially you got to imagine, I think it's like a toilet roll, right? Like an inside of a toilet roll. Have you ever opened one of them up? Do you know what shape you get? Yep. You actually get this shape. Okay, so this is toilet roll, and if you twirled it round, into this shape, it's essentially what you've got. So you've got a right angled triangle here, and if we just slice that down the diagonal, so essentially we're only talking about the bottom half of this journey. The ball travels just straight down that diagonal. That's the distance it travels. But if you curved that around, let me try my best to draw that. It looks something like this. And then sort of around. That's really bad. Maybe it's a little bit further down, something like this. It's pretty tough. You got to imagine, and I'll maybe I'll do some animation here in the sense that the ball's gonna go down this way, and then spinning around as it goes, and then exit that way. But if you do that experiment, you can make it, right? So you get a bit of paper, draw like a triangle like this, and you can spin it around, like you can curve it into what might be some sort of cylinder, and you'll see. Anyway, enough of that. This is useful because this is the length of the ball. And what would the 12 represent? That's from where it started to where it exits, right? So the 12 represents the side of the triangle here. And what does the 8 represent? Nothing to do with this, really. But hopefully you can see that when the ball went in, it did a full circle around the circumference, because when it went in, it was the same that went out. So this here is the circumference. We can use this as the diameter to find that. So if you remember from previous time, when we did circles, how we find the circumference is 8 times pi. It's pi times diameter. So this down the bottom here is essentially 8 pi, which I'm going to leave like that. If we're doing higher paper, we should be more comfortable to use pi in our working out. It's so much easier. It's a button on the calculator. So where are we going? Clearly, this is going to help us find the distance that this pinball has traveled. And it's Pythagoras all the way. So Pythagoras, for finding a long side, is in addition. So this is my 3D Pythagoras question, and I hope you like it. It's visualizing the three-dimensional side of things. But this is the real tip for 3D Pythagoras. Just draw the triangle somewhere else, like a normal triangle. So we got 12 squared plus 8 pi squared. And I realized, as I just said that, sometimes that's the hardest thing. It's spatial awareness, being able to visualize these things. The ways to improve spatial awareness would be doing sport, video games, Lego, anything that has some three-dimensional element that you're involved in seeing all sides or have an experience of three-dimensional shapes comes from very unlikely places. And there's no better time to start than now. So maybe buy a Lego kit. Funnily enough, I am obsessed about Lego myself. I have a few videos on some of the best Lego kits and why they're so good for you. You can check them out if you want to, I don't know, maybe some trivia to impress people with. Now, we're going to use Pythagoras, as we said. We're going to label it x, so we've got a focus. I need to start using x properly because bad habit. And what do we get? Well, square root of 12 squared plus, I'm going to be putting that in brackets, 8 times pi squared is, not bad, 27.85. Sadly, can't leave this as a nice fraction. 57776. Now, this was in centimeters because this is what we're using so far. Now, if you're going this many centimeters per second, you're not going to spend very long in that tunnel. So as a bonus on top of this, we actually have to figure out how long that's time. Okay, the time where the player does not see the ball. And it seems as though here we have a speed. So hopefully you're getting, sorry, this is distance. Hopefully you're getting that we're having to do a speed distance time. Like this. And so speed equals distance over time. But if we rearrange for time, time is distance over speed. We need to make sure they're in the same unit, and they are, because this is centimeters over here, the distance, and the speed is in centimeters per second, meaning time is going to be in seconds. So it's all written down, really, if you know where to look for it. So the distance is 27.85. Golly, was that a 0? Sometimes the zeros on here look like a 6. I must apologize. If it wasn't, and this is going to be slightly off now, I apologize. That's all I can do. I think it's a 0, so we'll go with that. Divided by speed, which is already in the correct unit. And our answer is going to be, I'm going to keep it on the calculator here, that's nice and easy. Our answer is going to be in seconds, divided by 2682. Okay, 0.0103 seconds. And nobody could do anything with all of that. We're just going to call it this and round it to 2 decimal places. So this is how long the player doesn't see the ball for. Okay, hopefully that was pretty awesome. If you didn't get that one, I bet it was because you didn't know it turned into a right angle triangle. So there you go. Hopefully that's all in the bag. Okay, a very important button is in the shape of a right triangular prism. I can just about imagine a button that looks like that, as shown below. The button needs to have a red phosphorescent, okay, so that means it glows in the dark, cross tape on the top. It's so important, it must glow in the dark. From B to F and from A to E, as shown in the diagram. What is the length of the tape needed? Okay, so in this instance, we'd be looking for something we could work with, but I think the key here is knowing that this shape, that's ABEF, is essentially just a rectangle. Okay, so let's write it out again, ABEF. And if we draw just one of those lines, hopefully we could see that that creates a right triangle. Yeah? And it's exactly the same distance from here to here, which also creates its own right triangle on the other side. So if we focus on just finding one of those lines, we can double it. We have one of the distances, it's 1.6, but we don't have one of the others. Okay, so we don't have this one, which would be what we want. This one is tied into this triangle on the side, which is a fairly straightforward triangle to see. It's definitely right. So we will draw it again, as 2.4. The height we gather from here. And hopefully you can see it's a matter of Pythagoras. So we'll call that y, and the result of y will be on this top part of the button. So how do we do that? Well, y is equal to the square root of 2.4 squared plus 0.8 squared. So there's 3D, well, it's kind of 3D Pythagoras, because it's a 3D object and you're doing Pythagoras, but nothing that you can't manage. Let's figure out what this is. And by the way, I don't have the answers in front of me when I do these questions. I'm actually sometimes very happy that they work, because I design them and I think, yeah, let's have a go. I do somewhat check some of them, but not this one. This one I was pretty sure, as long as it was a real 3D object and the dimensions are not impossible dimensions, that we could just try and figure it out together. So I'm as excited to find these answers as you are, or frustrated enough to find them, as the case might be. This is the value of y, and this is now going to lead into our equation over here. Hey, anomalies. We love anomalies. There. So what's going on here? We need the hypotenuse. We're going to call it BF. Best friend. Whatever. Or FB. I'm not going to say Facebook. What are we doing? Yes. So we've got 1.6 squared plus this horrible thing, 2.529, and that's why I've kept it on the calculator, because I don't want to I don't like type it out again. It's just quite a big effort. It would like spend a lot of time. So I'm ready to use that now as an answer button. Essentially, it's going to look like 1.6 squared plus answer squared. All right, so let's do it. Square root of 1.6 squared plus answer squared. Lovely. 2.993325909. I'm not going to round it as we go along. Really little point. And it always leads us to try and use the easiest rounded numbers in the working out. Recently been marking some exams and people have been using rounded numbers. Just please round at the very end only. Otherwise you get the answer at the end wrong. It's kind of sad, and you deserve those marks. So what have we found? We found one of those lines. That's BF. Okay, let's just write BF. Now, without having to recalculate anything else, AE is equal to BF. So AE plus BF excuse me, equals 2 lots of BF, which we could just times by 2 on a calculator, because we've got it up. 5.9866651. Let's give them some more space. And this is the length of two phosphorescent lines, but that's it. And does it ask any, did I bother to do that? Like, what accuracy? Nah, let's do something sensible. So if we're measuring tape, and this is in centimeters, 5 is okay. Like 5.9 is okay, but 5.98 is not okay. I mean, like, there's only so much you can do, right? So I would say 1 decimal place for millimeters. And if I round it, that's going to go up to 10 and make that 6. So we're going to say 6 centimeters. And, you know, in real life, you'd have a little bit extra you can cut off. It's nice to have a little bit extra, right? That's to 1 decimal place. I include the 0.0. Don't be shouting at the screen now. I include it because I've told you I'm giving it to 1 decimal place. But sometimes this is the way the cookie crumbles. You get this strange thing. You have to be able to deal with that. And that's 6 centimeters. So essentially we're giving 3 to both of these. Nice work. I love these things. This is 3D Pythagoras. So yeah, we've done a lot of this stuff. What about it? This is a ratio. What is a ratio? Don't be scared of it. A ratio can be many things, right? It could be 3 to 2. But a ratio can also be a division. So literally, what we have up there, divided by 3, is a division. We're talking about two quantities and how they relate to each other. That's a ratio. So knowing what we know about trigonometry, the angle x in the following diagram has a tangent of 4 over 3. Okay, so tan of x equals 4 over 3. That's what we're saying. And we need to find the value of y. So in this scenario, if we were to apply trigonometry, we would say that tan of that angle is equal to the opposite over the adjacent, which is 9, like this. Well, it seems to me like we have a fraction which is equivalent here. So tan of x is equal to y over 9, but it's also equal to 4 over 3. So if we equate these two here and we think about this, we can see that if y over 9, if we write the fraction on the right in terms of ninths as well, that means we've multiplied it by 3. And we do the same to the top, and we get 12. So y equals 12. That felt a bit weird, right? Because in class, you may have been told that you know how to do trigonometry because here's all the nice numbers and put them into a formula. But this really shows, do you understand what's going on with that triangle? And can you apply it in a situation which is unfamiliar? However, if you got that on your own just fine, congratulations. You're going to do great. Right, the last one is going to be bearings, and it gives us an opportunity to look at parallel lines, trigonometry, Pythagoras, a number of different things. So in this regard, we should get started. I think this requires a little bit of a diagram. So as we talk about it, we can mark it on. So I had to blow this up a lot, and therefore we can't actually see the question. But we start at the emu plane. Yeah. I'm trying to use a mouse to write, but I won't. Let's use this. Yeah, that size. There, that'll do. Start the emu plane for 42 kilometers on a bearing of 0.95. So this is to Farneyhurst. Now, whatever it actually is, like, I'm not even interested really. Oops, let's do this, otherwise that will not look good. I'm not really interested too much. I'm just interested on the fact that it's telling me, like, do I care if it actually looks like it or not? Yeah, so as you can see, I'm using a program in Windows that's no longer supported. It's supported on the tablets, but not in the Windows app. So it has this really strange thing. And if anyone who developed this is watching, what are you doing with this? Like, let me turn it off. You know, the function that says I'm going to auto place stuff to maybe corners of shapes. Like, sometimes it's impossible to get around that. Anyway, we might see more of that as we go forward. And I think what's really useful here is to draw if it will let me, a horizontal line. Oh, that's ridiculous. It's like, I think you meant this. I'm like, no, that's what I meant. I know what I wanted. We'll leave that there. We'll pretend that it's, in fact, maybe if we undo it, it looks better. I think that was straight. And we'll draw one in going up the top as well. It's going to tell me what it thinks I wanted again. And I'll just tell it No, sir. All right. At least that lets me be quite accurate after that. Let's fill in what we've got so far. This thing here is 5 degrees. This is 90. And when we're at Fahrenheit, in fact, wherever the hell this is in the world, we're then going to go, what does it say? Let's go to the top. Reason why I said that was 5 degrees, because this is 90 and it's sort of 5 degrees. We measure bearings from north, and this way being north, which I probably should have put in the question to be fair, but happy for you to assume that this way was north. And for those hardcore people out there who would want to research where this is in the world, it's in New Zealand, and you'd probably realize that that way was north if you were really going for it, and maybe you deserve a prize. Pat on the back, go for it. Now the next step is what happens. So this UFO has gone from the Emu plane down to Fahrenheit, and then it suddenly changes direction and shoots at a bearing of 040 for 34 kilometers to Stag and Spey. All right, let's do it. Doesn't matter where I draw this right now, I'm going to have to change it. Yep. Typical, but I don't mind. We're having fun. So let's just say that's 40 degrees, like that. There's a couple of other things that would be really useful to have at this point. One would be another vertical line. Let's get it in over here from Fahrenheit. And I think another vertical line would be useful to Stag and Spey, because we don't know really what's going on there. So we've got a lot of things happening. Let's label some degrees. This here is 40 degrees because it says bearing of 040, and then this is north, so we're going to be measuring from there. We've got some distances, haven't we? So it was 42 kilometers to the Emu plane. Hello, anomaly. And it was 34 to Stag and Spey. Diagram not drawn to scale. Or distances believed. Where are we doing? What are we doing? Our aim is to... Well, first let me do this. Yep, good. Our aim is to... So that's where it gets shot down. What distance and on what bearing will the UFO recovery team have to fly by helicopter from the... So that means they're going straight there. They don't need to follow the roads. From the Emu plane to go directly to Agent Moldy to assist with the recovery. If anyone's a fan, by the way, right, you know what I mean? Agent Moldy. If anyone is a fan, yep, that's for you. How do we go? So let's have a look. Let's add in one of those crucial line. We'll call it the exam line, which we're going to have to change anyway, so whatever. Oh, beautiful. That's exactly what I didn't want. Thanks. Thanks again. So essentially, this line is what we need for this question. Now, I'm sure there's a real smart way of doing this, but when I designed this question, I was just thinking about a scenario and thought, let's give it a go. So I can't actually tell you if there's a much more neat or elegant way than beyond me just starting it here as if I was in the exam. It's like my first thing would be to look at if I had any other information that I could gather from this. So I'd be adding in little markers where I could. That's a 90. So we've got a right triangle here. Essentially, if that's 95, then this angle here is 85. Why is that so big? Not good, not good. Let's 30, try that. That's nice. 85 degrees here. Useful. You know what? I could see another right triangle, but I'm going to have to add a line. It's going to be horrible, but hey, so close this time, isn't it? So close. Let's do this one first. That's good enough. Is it though? Is it though? It's got to be parallel with that blue one. Maybe more like... That'll do. That will do. Okay, so essentially this line is parallel. Oh, I've still got it in special mode. Yep, let's do that. This line is parallel to that one. And this allows me to see another right triangle here, but also here, which is very interesting because this distance across here, let's call it y, is the same as this distance here. And if I want to start seeing that red line in terms of right triangles, it would be nice to have this distance here, which is x, and this distance y. So let me just draw this out at the side so you could see the plan. There's y and there's x. It would be nice to know x and y. And then there's a distance, there's z. Because if I have those dimensions of the right angled triangle, I can do something with that. Finding this angle would also be useful. So I'm feeling like, I feel this is possible. I also feel that it might be trigonometry in the end because we've got an unknown angle. I feel like the plane of attack is going to be from this triangle down the bottom first. Okay, so this triangle allows me, and that's this one here, because I have like all the angles and one of the sides, so I can do something with that. So let's draw it separately. So essentially, maybe I can use this. If it doesn't work, I'm never using it again. Ah, beautiful. Thank you. Essentially, label it, because if you're going to stay on that diagram, it's going to confuse the hell out of you. 85 and 90, and the aim is this. So what should we take for the focus angle is our question, really. I'm going to take 5 degrees because it was given to us within the question. And I'm just going to move that down a bit so we've got some space. Essentially, we can label this as the opposite, hypotenuse and adjacent. And we're looking for working with the adjacent and the hypotenuse, so that's going to be cosine. So cosine of 5 degrees is the x over the 42. And so x is equal to 42 times cosine 5. Remember, in these questions, once you see me do it, you will feel, wow, that was so easy, I could do that. The hardest part is knowing what to do, right? So when you're in that stressful situation in the exam and you've got all these other questions to get through, knowing what you're doing is often the hardest thing. So staying organized is the solution. So I'm going to, as much as possible, be drawing like separate areas here and try and keep them organized on the page. Let's see what that looks like on the calculator. So 42 cos 5 is 41.84017732. Love that. 732. Nice. We're on our way. So that's x. And what do we want to do now? I think the next part of this lies in the triangle here. Now, how can I make this clear to you? I'm going to circle the vertices of this triangle. Here, here, and here, here, and here. So essentially, if we can find the distance y, that's going to be the same as up here, which will complete the bottom of that triangle. What dimensions do we have for this triangle? We've got the unknown here. We've got this entire length here, which is 34. And maybe we've got a little bit more to be had. Let's see where we're at so far. Let's draw that triangle down here. And hopefully it's going to play ball again. Yes, sir. Okay, so We want this one. This one is, what a memory, 34. Anomaly. Must be the alien. And we want to find different angles, right? So essentially looking to looking to figure out what sort of stuff's going on with different angles. I mean, we could look at this one here. I'm just playing around here. That's definitely 5. That doesn't really take us anywhere. Oh, that's useful. Because this is 90 degrees in total, this one here is 40, so this must be 50 degrees. Super useful. Like that's the one that we need. And now 50 plus 90 is 140, so we know that this is 40. It might be useful to label that in a diagram. I don't know if it's, hello anomaly. I don't know if it's going to be useful later, but you never know. Oh, that makes sense though. Look, see the alternating angle? The alternate angle there with the parallel lines. Yeah, saw that one coming. I'm not going to make that diagram too complicated because maybe we don't need to. All right, so what would be really cool as well is to find Z. But we can deal with Z later. Interestingly, if this line here crosses, this doesn't look, I mean, it's right because that 40 shouldn't be there really. That's why it's confusing. But essentially the 40 should be this angle here. Should I get rid of that there? Try and squeeze it in. That's why it'll be confusing otherwise. This is 50. And the principle there is if you have two parallel, you have two parallel lines like this, and if a line crosses a straight line, then it's going to cross the bottom parallel line at the same angle as the parallel line like above. So this is 50, and so that's 50. That's where that came from. That's really useful because if I want Z later, that's just this top triangle. All right, we're on our way. Let's take this home now. So, we're going to first find. What we're going to first find? We can find cosine of this side. So let's get some space. That should do. And we're going to see that cosine 50 is equal to the adjacent, which is y, over the hypotenuse 34. So y is equal to 34 times cosine 50. Let's get some calculator action here. That is going to be 21.854777873. Right. Very useful. Now, if you need a little bit of a reminder, these are in kilometers. So it might be nice to have that written there. That's so useful. Okay, so that's about 21.85. Darn it, there's a lot of anomalies tonight. Must be the theme. And we also want, no, that's a different triangle. We can't be doing it based on that triangle, though a lot of these values are similar. Anyway, we'll do that when we get to it. So we've got the y. Let's start filling this out here. If we add those two values together, x plus y, that's going to be 63. So let's move up here and put it on here. 63.6949 5605. Lovely. Move that a little bit. I know it's a lot. It's a big number to take in, but then you don't need to put in a calculator again. The next aim, We haven't got any of these others. The next aim would be to find Z, I suppose. What do we know about Z? It's a pretty tough one, I'd say. We don't have the 34. We do have the angle, but that's not going to be based on that. We could definitely find all of it. Could we find that? Yeah, that's a long way around. That's a long way around, but we can do it. Right, so back to this triangle here. If we found this, I mean, I'm on the spot here, so maybe you could see somewhere better, but you know, where there's a will, there's a way, right? So this is the side that I'm going to call, gosh, well, I'm running out of stuff here. I'm going to call it mu. And that would be the same as the height of this triangle here, which is the opposite. And I'll use the hypotenuse again. So I'm going to use sine. So sine of 5 degrees is equal to mu over the hypotenuse, 42. So mu is equal to 42 times sine 5, which is not very much at all. 3 clicks, 3 kilometers, 3.6605 Marvelous. All right, so we've got that height. That means we can use this top triangle. We could use that whole triangle to find, yeah, so we want to find this, the whole thing here, which we're going to have to give another letter. What letter we got? I don't want to use pi. Just thinking of those. Let's use beta. Okay, so let's say that this one is beta. It would be nice to find it. We would probably want to be using, maybe we'll use sine again, so it's opposite in hypotenuse. So sine of 50 equals, let's write that a bit better. Sine of 50 is beta over 34. So 34 sine 50 equals beta. Like Peter from Hunger Games. Peter. And let's turn it into a decimal. 34 sine, I mean, you could use 34 sine 50. It's kind of neat, actually. Beta equals 26.04551107. I've learnt my mistake. Make sure that the numbers are clear before moving on, because I may question them later. So we should probably reconvene our troops and see where we're at. That in total thing, so beta is going from the Stag and Spey down to Hawkswood, is 26.04, but we just want Z, so we need to take away the value of mu. Where's mu? Mu's over there. Right, we could do this. So we've got that on our calculator. So we're going to take away 3.6605411195. And lovely, we found the value of Z. Time to move this triangle somewhere else and continue on with the dilemma. Maybe like there. Okay. Got it in our calculator. 22.38496. These are the numbers of our destiny. They're going to take us to the end of the question. Now, essentially, we're looking to find this hypotenuse. That was going to be the distance. And that's going to be Pythagoras, right? So not going to waste time on trigonometry if we don't have to. So the two small sides added together, 22.38 ... And I could keep that in my calculator. What are we calling this? The final, we'll call it capital F. The final distance for the helicopter. Could call it H. I prefer H. H is probably my favorite. No, it definitely is my favorite. letter out of the two. H, doesn't matter what letter. Moving on. Keeping 22.38 in the calculator, we can square that. In fact, I'm going to square root first because it keeps the structure quicker. Plus, now this is where we have to go back to do the full number. So you have to use that full number, not just the number I've put in there. So in brackets, 63.69. So yeah, this is what it's like in the exam sometimes. Trying to stay organized in a chaotic space. And drum roll, 67.5139. 5635. What would be a nice rounding here? Maybe 67.5 clicks. 1 decimal place. This is the distance that the helicopter needs to travel. The last question we're being asked is the bearing. Now, the bearing is based on north. So I'll just draw it roughly. There's north. So essentially we want this angle. So we'll call this first one angle 1 and this angle 2. A quick double check to see if we don't know it already. It's an alternate angle with this one. I don't think we know that one. Just double check. I don't think we work towards that one. It might be a clever way of doing it, but let's just assume we don't, because I've got a different way in my mind. We're going to use trigonometry here for the last time. We're going to use tan, because if angle theta 1 is our angle, and then this would be the opposite, that would be the adjacent. So we're going to say tan of theta 1 is equal to the opposite, 22.38 didit over 63.69 didit. So that theta 1 is equal to, oops, sorry mouse, give me some space please. Oh no, no space. Okay, much space is possible then. Yeah, that'll have to do. Inverse tan of the above, 22.38 dot 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 over 63.69 eek dot dot dot. Theta 1 equals. Yeah, this is the painful part. Bear with me. Processing. Close that bracket at the end. Did you get 19.363 52675? Hope you did. And this is theta 1. We want theta 2. So we just have to take it away from 90 because that's a 90-degree angle. So 90 take away theta 1 is equal to theta 2, which we can keep in our calculator. 90 subtract answer. And yeah, running out of space. 70.636. We don't need to go much more. Degrees is theta 2. We just need to turn it into a bearing now. So theta 2 as a bearing, well, let's just not write that, we don't need to. The bearing would be 071 degrees. Because, I mean, how far out are they going to be after a long time? Probably a long way out. You could give further decimal places depending on how accurate you want to be, right? But let's just round it to this. You do need to give at least 3 digits. You could say 071.6, but I'm going to round it in this way. That should be good enough. And my distance in the brackets here. Ooh, oodalali. That turned into a much bigger question than I thought. What did we use along the way? Multiple cases. We've got Pythagoras, trigonometry, and I think the hardest part is staying organized about what we needed to find. You know, because look at all these lines. And the way I coped with that was to have these separate diagrams. And that really helped me focus on those individual points to think, what do I have? What do I need? What can I do? And slowly and surely, the diagram got filled out. Even Pythagoras along the way, eh? And finding an angle and a bearing. Great stuff. Oh, and parallel lines, right? So a little bit of work on that. That's it for this week's questions. And we've been covering the topics of Pythagoras, trigonometric ratios, and bearings, all in sort of a few concise questions that are very similar to some things you might see in the exam, and definitely things you've never seen before. So give yourself about half an hour, and the next week's questions will be up, and you can give yourself a jolly good go with those. And I'll see you next Saturday at the same time. Last announcement, please, 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 if you have another question, I've made next week's question slightly shorter. So if you have a question, get it to me by Friday and it will go in here and we'll go through it. If it's something that you just can't figure out and you'd love to know how to do it, full solution on Saturday. Anyway, it's great to have you around and I hope that was useful. Just going to say goodbye and hope you've had a great week and have a great week ahead. Make sure you stay working hard and all the best.